Hello all, this is HomoMongo Project Part 3. Encryption of GeoJSON objects stored in NoSQL databases. The concepts of NoSQL MongoDB. I was an SQL database administrator in my country, so I was quite advanced in databases. Though Part 3 was the hardest, it was actually easy for me to do based on experience. Here I only intended to explain briefly the reason for the schema of HomoMongo Project encryption that I came up with. First, it is important to note that all databases can retrieve data. But unlike SQL databases, which run structural queries, NoSQL databases are not arranged in tabular forms with rows and columns to have attributes with common relationships. NoSQL simply dumps data into a document. A single page can be considered to be a collection. A collection can have a set of objects stored in rows. So the strategy of this project is completely in agreement, as most encrypting methods recommend the use of the same key for encrypting and for decrypting each set of collections. But as MongoDB stores each JSON object with a unique ID per row in a collection, this project does not agree that you must always retrieve all the data in a collection to decrypt them, as it is a fact that objects in a collection can be or referenced by IDs. We can choose to selectively decrypt a single object only. So this is the schema that was recommended. As you could see, after our private network subscribed from Owntracks and it arrived at the internal Mosquitto broker and sent to Node-RED, it is then encrypted and sent to Atlas. But while it is being encrypted and sent to Atlas, we have an internal database that we can be able to store the object's ID and maybe the data for references. Anytime we are now retrieving data from a single collection, we can program our algorithm to decrypt just only the payload for the object that the user is after in that collection, and we are interested in singling out just one item for the user to view. That is taken care by the decrypting function. Thank you. Now this is the completed HomoMongo flow on Node-RED. First, the Owntracks publish it to the public broker. I put this just for reference sake. Then our MQTT subscribed the message. The message first is now encrypted homomorphically. But the problem is a GeoJSON data, when encrypted, will be converted to strings. So part of the encrypting function is I have to convert from strings to a JSON object in order to be accepted by MongoDB. This was the challenge I faced while choosing an encrypting algorithm. Of course, there is algorithm out there on the internet that does all this automatically, but the researcher will not learn if you do not know what you are doing and how to create and model your own encrypting algorithm. So I decided to use a simplified version in order to explain how it works. So this is the encoding algorithm. These two parts are it: encrypt, convert it to JSON object, to be accepted by MongoDB, and here we can debug whether it is successful. So we now use a method to retrieve data from our MongoDB, which is HTTP GET method, or we can use HTTP POST method to post in data, but we are concerned with retrieving data from a collection. Now, when the data is being retrieved from the collection, we can view it with a HTTP response. I added this just to debug what is happening. So we see all the payload of the data coming out of the MongoDB. But here we have to do something similar like our encoding algorithm. This is our decoding algorithm. We have to use a per se JSON stringify method, and then to convert it to strings, then we decrypt it back, and then we debug the payload successfully. And our decrypting function here can selectively decrypt just a single object ID from the payload collection, because there could be up to 10 or more objects inside one collection, but we want the viewer to view just exactly what is intended for them to view in the collection. So the decrypting algorithm can be modified to only decrypt a single object, which I demonstrated in this program. And then we debug. One last thing, we could also create an internal database whereby by the time we are sending this payload to Atlas MongoDB on a public server, our internal database is keeping reference data of the object ID that was sent to the MongoDB, so that when we are decrypting it, we can selectively specify the algorithm for the user to decrypt only what is intended for them. Homomorphic encryption enables computation directly on encrypted data, is probabilistic. Semantic security is a requirement for enabling homomorphic computation. Problem: it can only efficiently enable polynomial operations. Probabilistic encryption. Random sort added to each encryption to achieve semantic security. You could see that in a homomorphic encryption using a probabilistic method, which make it more difficult to decode. A plain text is encrypted by the public key and then ciphered. The sort means it is added randomly so that the plain texts are not disclosed, and the equality of plain text cannot be determined with non-negligible advantage because it has been mixed up. Now it is computed, and then we can now cipher and decrypt it with the secret key, which is an inverse operation to get back the plain text and send to the receiver using quantum homomorphic encryption. So I am doing my thesis on quantum homomorphic encryption. It is not yet approved, but I seek the university for understanding the implication of quantum computer on cloud computing data, the concept involved in quantum key distributions. I'm going to use it in this project to explain the advanced threat we face in our IoT cloud and how it can be boosted up to include the principle for quantum computing. Quantum key distribution creates an OTP one-time password. Using the principle of OTP in quantum key distribution, the key is really random Quantum computer is started as really generating these keys randomly more than classical computer, which might use an algorithm to create it, which in essence is not truly random in the ultimate sense. But quantum computer uses quantum mechanics to generate these keys randomly. Second principle, the key must be as long or longer than the plain text. That is, the key length must be 1 time or 2 times or 3 times longer than the plain text it is encrypting or more. 3. The key must never be reused again in whole or in part and totally kept completely secret. Then the resulting cipher will be impossible to break. It has also been proven that any key with perfectly secret cipher properties must use the same keys requirement as that of OTPs. So this is the recommendation of the algorithm that we will create for HomoMongo project, or should be used, even though some of this method is way beyond the scope of the project, but it's part of the recommendation that the keys created must be kept secret and also hash or encrypted themselves, which is the concept of quantum computing I am bringing into this IoT project, which quantum computer can handle. And then if we can include quantum computer into our IoT project, it will be good. Right now I have researched, and you can make a request via HTTP to the quantum server using QASM programming language, which you embed in your JavaScript. So we can have a backend that is doing the encryption for us on our IoT cloud project. Actually, the OTP is started to be NP complete. Well, in a sense, you can't be sure anything is NP complete. Nobody is really sure. If one of the principles is broken, then the principle has been compromised. And why is that so? Let's look at SAT Boolean satisfiable problem, which is the first NP complete problem proved by Cook. What is the idea we learned from that? That what the OTP precaution is taking into consideration is that if you can prove that a problem is NP complete, you can proudly say that the polynomial time solution is unlikely to exist, and so there is no efficient algorithm to solve it. All decisions arrived at could equally be true or false at the same time, so you are simply taking computers Turing machine out of comfort zone to model things mathematically with any degree of accuracy. Traditional versus homomorphic encryption. The traditional way of securing our data has to be on consistency and availability. The emphasis on NoSQL is on access control and authentication. Role-based access control to create a user administrator first, then create additional users, some with lesser role privileges. Encrypt data communication via TLS, SSL for all incoming and outgoing connection to MongoDB. We also limit network exposure by allowing only trusted clients IP to access the network interfaces and ports on MongoDB instances. We can create audit system activity to track user access with changes and record system events logs. We also can encrypt and protect data locally on MongoDB, just to measure but a few of the traditional method. But with modern security risks, the motion for homomorphic encryption is that while the traditional method was helpful in time past, no doubt, it has become increasingly necessary to look at protecting our network itself, especially with the threat posed by the quantum computer age and 5G high-speed and huge bandwidth network. The threat of using traditional method alone when systems are being hacked in mass and data decrypted is no longer worth it. So encrypting our data homomorphically before transmitting and storing them, though may add unnecessary overhead payload, which should be mitigated by the 5th generation high-speed systems and networks anyway, is now an option more suited for today's distributed system on IoT clouds. But when combined, the traditional and homomorphic encryption together for better protection is more suited for our IoT cloud security today and can give more added security. Thank you all. And this is the HomoMongo project flow for the encryption. Already we have seen how the MQTT subscribe was configured, so I won't repeat that. I'm coming to the encryptor. This node is the algorithm that encrypts the data coming from the MQTT subscribe, and the data payload is JSON. And when you log in, you could see the password. In line with OTP principle, I wanted this password to be longer than the strings we are encrypting. Averagely, the string should be between 200 to 250 words long, but this string is 500 words long and is not human friendly but machine generated. Let me show you what I did. I came to this website out of fun and generated it. You can specify how long you want your password to be. I choose 512, which is very long, and I click generate. It generates it here. Then I copy it. So take a look at how it is. You could see it's not human friendly at all, and it's very long. Okay, that same key for this encryptor is the same key you use to decrypt it. But for now, let me concentrate on the encryption. Now I remove this so that we can see how the sending it to MongoDB directly, how it will not accept it, because when a data is encrypted, it is converted to strings and MongoDB will not accept it. So I deploy. I want to go to my MongoDB Atlas. I have not created any collection yet. I come to network access. When I was conducting the experiment yesterday, I come to set my IP address. Yesterday it was 161. I have to give it permission here, but today when I check in my browser, it has changed. So to avoid this, you can give access to a client here. But for this project, to avoid any inconveniences, let me just allow the client access from anywhere, from any IP, Look at it, it's 00. Let me enable how long it will last. Let me say 1 day. Let me put it 1 day. Confirm. So this is not good for security, but because I'm doing this project, I want to use it so that I can speed up. Good. So let me go back to the cluster. Good. And let me go to collection. So now if I receive any data, I will come here to confirm. So I deploy. On my tablet, I come and publish waypoint. Can you see? It's not accepting it because the JSON object is converted to strings. And here is the encryption, a very long strings. So we have to convert these strings here. We have to convert it to JSON object with an ID. So what is inside here? A simple function to convert and give it an ID. So I go back and insert it. So I go back and insert this function. I clean the debug button, and on my Owntracks, I set the Geofence 950 meters so that I will use it for this experiment. And so now I deploy. I come to my mobile phone and click publish waypoint. You see, it successfully embedded the object, which is encrypted and sent to the cluster. Look at the object ID here. So let's go to the collection here. Let me refresh the page. The object has arrived. Can you see that? The object ID, and it is encrypted, as you could see. Good. It is encrypted, and we can take a look at how I configure the MongoDB. If you come here, I don't have to disclose my password. This is the API key, this is my name, password, and this is the cluster. If you go down, can you see that? Good. Here is the name of the collection, GeoD. So good to go, and you could see the data that was saved. It's in the collection called GeoD. So I have demonstrated how it was encrypted. Now let's look at how it is decrypted. Now let me decrypt the data. The first button here is the get method using HTTP get. This is the get method. This is the URL. And this is the name of the collection, which I copy. you can open another page here at localhost to view the HTTP GET request when it loads. Okay, this is the response, nothing else, and this is the JSON stringify method that will be decrypted and debugged. So let me connect it and deploy. This as we are no longer using this, I disconnected it from sending any data. So we are only interested in decrypting from this database. One more thing, when you come to this data, you can see this object position is at 1, this object position is at 2. So we can come here and specify the payload, the object position at 1 for it to debug it. Deploy. So we have to refresh this browser to request the HTTP GET method. Okay, you could see that it has retrieved the data, but when you come here, it completely decrypted it. So here we just want to see the payload that came from MongoDB. As you could see here, it is encrypted, but as you could see here, we decrypted it, and I only decrypted one of the object, and it is the object with 800 meter radius, which is this second one. So if we want to get this object out, we have to come back here and specify the position of the object 0. Then we deploy again. Let me clear the debug button. Let me do the GET request. Can you see the second one is 950? So the user is only seeing what the algorithm specified for them to see. Even though the data came in, you can see the two payload came in, the first payload, the second payload, but not all of them were decrypted. The only one which the user requested was decrypted. So the recommendation is that when you create on your server side, then the user can only read what you specify them to read based on how you deploy the algorithm over the network, which will be keeping track of the object position, which you can have in your internal database, which the algorithm can be using. Thank you. This is the end of HomoMongo project. I thank you all. Thanks.